Welcome everybody. Today we're going to talk about a new idea called the center of mass, which, as you can see from this definition in the discrete case, is a weighted average where I take the position of each discrete object in my system, weight it by the amount of mass that that object has, and then divide by the total mass of the system so that I get back a quantity that is still a position vector. And we're going to talk through this definition in a few simple cases. The first one is I'm going to think about the simplest case I can imagine, which is if I just have one single point-like object. For an object like this, I only have one thing in the sum. It has all of the mass. The masses cancel out, and the position of that object is then going to be the position of the center of mass. You'll note that the center of mass position, like other position vectors, depends on my choice of origin. So for a single object, if I want, I could put my origin at the initial location of the object, and then my initial center of mass position would be 0. But I don't have to make that choice. If I extend this to thinking about two discrete objects that have the same mass, I can now think about what this equation is trying to tell me, especially in the context of different possible origins. So a straightforward origin to pick might be one of the objects like we saw earlier. At that point, what I'm doing is taking the position vector of this object, which is 0, multiplying it by the mass of this object. And then I would find the position vector of this object, which is shown here, times the mass of that object. And then I have to divide by the total mass. And if the two objects have the same mass, then what I'm going to do is take this position vector for the second object times 1 unit of mass, but divide by 2 units of mass, meaning that the position vector is going to be, for the center of mass, halfway in between, which should be relatively intuitive. If I have two objects, each of them having equal mass, then I'm going to expect that the center of mass is between those two objects. Similarly, I could think about what happens if I have two objects but that have unequal mass. Maybe this one has more mass than the one on the right. And if I do that, again, using the origin as the position of the first object here, I get 0 contribution to this sum from that expression. When I multiply this position vector by this mass and divide by the total mass, I'll now get something that's a little bit bigger than a half. Maybe this is 2/3 of the total mass of the system, and this is 1/3 of the total mass of the system. And if that happens, then when I divide, I'll get a new center of mass position vector that is a little bit larger than halfway and starts to tilt in the direction of the second object. The last case that I can extend this to is an arbitrary collection of different objects, each of which has its own mass. So I could go label these M1, M2, M3, M4, M5. And then for each of those objects, I'll need to figure out the position vector relative to some origin, something like this. I would need to label each of those position vectors, weight them all by their respective masses, and divide by the total mass. And that will give me the center of mass